Okay, this is Lab 3 black hole orbit. The objectives are given position, time step, and mass of a star, which is orbiting a black hole. We're also given the black hole's position. We need to calculate the black hole mass, which we obtain with Newton's second law of gravitational universal gravitation. So we do this after analyzing the given position data. We're going to calculate a computational model of the star's orbit around the black hole. We're going to finally wrap up with what if and what does it mean answers. So we know the star data CSV file, the XY positions for the star. We know the star mass, we're given time step and the black hole position. So we need to calculate black hole mass. And the result was this, 2.495 e to the 31st power kilograms. That was confirmed on WebAssign. So these are the formulas. Magnitude of F net, which is net force, equals gravitational constant times mass 1 times mass 2 divided by absolute value of r squared, where r is the distance. So we're going to change around Newton's gravitation formula to get the second mass. So mass m2 equals magnitude of F net times absolute value of r squared divided by g times mass 1. R is the distance between the center of the masses of the star and the black hole. So distance r equals r2 minus r1, magnitude of r equals square root of x squared plus y squared, z is 0. Using Newton's second law to calculate F net equals delta p, which is change in momentum, divided by delta t, change in time, which is the momentum principle. We're using a small delta t to assume no change in force. So F net parallel and F net perpendicular, they add up to equal the net force. So another way of writing this is change in magnitude of momentum divided by delta t times p hat, which is the direction of momentum, plus the perpendicular component, that was the parallel, this is the perpendicular. Magnitude of p hat, direction of momentum, times change in p hat divided by change in time. This is the code. So initialize everything, and these are the system properties: the star mass, the starting position of the black hole, the position of the black hole, delta t, how much time we're calculating over the beginning time point. This is x and y positions for the star data, and we're creating lists to put in all the velocity xy components. So the first while loop is for the velocity, and we use Newton's second law to calculate net force, and we calculate the net force parallel and F net perpendicular. So the gravitational constant, and then this is the black hole mass, is equal to this formula: magnitude of net force times distance squared divided by g, gravitational constant times the star mass. So these are the arrows for the visualization, and yeah, so yellow is F net, blue is F net perpendicular, black is F net parallel. And so now we're going to run the visualization. There it is. Okay, now for the what if and what does it mean questions. What makes F net and its parallel perpendicular components similar or different from delta p divided by delta t's? They're similar since they're equal to one another numerically according to the momentum principle, but they're different conceptually. While F net is the cause for the forces causing the motion of the observed data, delta p times delta t is the effect, and which can be calculated from the observed position data. F net cannot be calculated. So what does it mean? If there was a new black hole but the star motion was the same as before, could you tell the difference The answer is no. The mass of the new black hole would not change since the motion, mass, and gravitational force all remain the same. Thank you.